Time for a pop quiz.
Come on,
Problem
Jeffrey,
solved.
you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
Zeta time zone logic, but math waits for no clock. You got some numbers to crunch or a question Zeta worth my time? Well, let's skip the chit-chat. Zeta trivial. If it's noon in New York, it's 5 p.m. in London, but who really cares? Focus on the math. Got any equations you need solving? Stop wasting time. Zeta careless. You should care about math. Prove your intellect. Solve Shinchi next to 8 tubers properly. Otherwise, your Zeta apathy will lead you nowhere. What's your correct solution? Zeta, ridiculous. Time on Mars doesn't compute with Earth's time zones. If you need math, let's calculate the gravitational differences or something concrete. No more distractions. Zeta, pointless question. Time zones aren't math problems. Focus on calculations. Got some equations or math that need solving. Otherwise, quit the distractions. Zeta, right. Time zones aren't my forte. I'm focused on math. Throw me some equations or let's skip this nonsense and talk real numbers.
Hi everyone, welcome on in. Today's a big day. We're going to be doing a big presentation for the art and reading group. We're going to be taking a look at general linear transformations and all that good stuff. Not set to start at 2, but usually we pop an announcement off in the reading group, and it usually takes a few extra seconds for people to kind of mosey on into the presentation, but if not, that's great. That means we'll just be presenting to all of you. And then it's super chill. Hope you're all doing well on this beautiful Sunday. Yeah, let me know what you've been up to. We can have some chit-chat while we're waiting for everyone to get set up over in Discord. So maybe what I'll do while we're waiting too is we can post an invite in case you do want to tune in or join the art and reading group. Let's see, where do people usually come in? They usually come in like in here, right? No, that tells us. I don't know. Have we? We must have given an invite somewhere. It's probably here. Maybe it might have been might have been way back. So Mohammed, if you're here and you want to post an invite link to the Simple server, you're more than welcome to do that. I mean, I've had a pretty casual Sunday. Woke up late, as I usually do on Sundays, which is fantastic. Did a little bit of video editing, so we're almost completely done the video editing arc. I have 3 more see a question, try a problems to post, and then probably 3 more videos to post that I have to edit that Joe's gonna make, and then we're completely done our course. So we're getting there. You'll see a few more videos pop in over the next couple days.
Why did you even rope me into this? Because he roped me into this. Well, him over there, he roped me into this. Well, he roped me
Hi,
into
Anders.
this.
Welcome in. Hope you're doing well. Hi, Stooky. Hi, Mohammed. Hope you're doing well. Yeah, please, you can do that right now. And Stooky, if you want to create an invite to the simple group server in the elements, you can do that as well. I just don't know. I don't know where to invite people to. That's all. But yeah, that's good. We should be getting ready quite shortly here, folks. So I'm actually going to go ahead. Let's turn off. Let's turn that off. And let's go ahead and we'll just pop that down for now. I don't know if we're going to be talking about dual spaces today, Anders, but we'll definitely be talking about, I want to talk a little bit about T-invariant subspaces. But I think, yeah, the conversation around dual spaces and kind of the direct product breakdown of invariant subspaces is better saved for a different day. But this is kind of the structure that we want to talk about, right? We want to talk about kind of a general transformation that goes between two vector spaces, V and W. And instead of mapping to the dual spaces, we're actually going to map to Fn and Fm and then kind of see what properties pop out inside those particular vector spaces, which are a little bit easier to work with regards to like matrix properties, right? Hi, Syntax. Welcome in. Girl called me honey and asked me to teach her mathematics. Am I cooking? I think you're cooking. You don't get that every day. You gotta follow that up for sure. All right, welcome in everyone. My name's Pencenter. You can call me Pencenter. That's my Twitch username. I go by Brian in the real world, so either or is fine. Stooky or Mohammed, if either one of you can just monitor the chat on Discord, that would be fantastic. I'll do my best to monitor chat on Twitch. And you're welcome to ask questions in either particular platform. That's fine with me. So the goal of today is to kind of get us through the last of the linear algebra sections in Arten. And I'm going to give you a little bit of flair on the pieces that I think are going to be important for you moving forward with regards to that. Arten's a mad lad, let me tell you. The way that he goes about doing stuff is quite wild. So I'm going to try to break it down a little bit more in a bit more of fine-tuned detail, so you can see some of the pieces that are happening. And maybe it's worthwhile for us just to start with a little bit of a recap. And specifically, let's take a look at what we remember about an ordered basis. because I'm going to need to pick up a little bit of information about what you guys know as well. And so let's call this be an ordered basis of a finite dimensional vector space. What has Arten delivered for you guys with regards to like thinking about dimension and thinking about bases and thinking about ordered bases? Is there some stuff that I need to know as I kind of walk into my Cole's Notes version of chapter 4? Like, what do you remember about a basis? Thank you, Mohammed. I actually did my hair today. Yes, it's true. I wore a nice shirt just for all of you. So from my perspective, when I'm thinking about basis to me automatically implies independence, so that these vectors are we call them linearly independent. So I'm going to say that each of these vi are linearly independent. Yeah, and Jeff has mentioned the other important idea of a basis, and that is that I realistically, if I'm thinking about any vector inside of my vector space, so if, well, we can probably, can I use the word span here? Basically, I want to say that the span of B should be equivalent to V as sets, right? So the idea is that any vector that I pull from vector space B, we should be able to write it as a linear combination of the vectors in B, right? So the idea here is that for any vector in our vector space, we basically should be able to find constants, and I am fairly certain that these constants are unique, so let's call them ki in the field that we're working with, such that we can take this V and we can rewrite it as K1, V1, K2, V2, and so on. And that's going to be an important piece of the information here that we want to talk about today. This idea of the uniqueness of these scalars is really important. And it allows us to do some really fun things when we start mapping stuff into Fn. Now, have you guys talked a little bit about dimensionality as well? So the idea that like if I can find a basis for my vector space consisting of n vectors, then we usually call the dimension of V n, like the number of basis vectors that we have. So that might be like another interesting thing to note here. So in this case, we would say the dimension of V is equal to n because we have n linearly independent spanning vectors in our basis. And I'm pretty sure it was Red that delivered the information last time. I'm pretty sure Red talked about how you can have this like larger set of vectors that still spans the space, but they're not linearly independent. They're linearly dependent. Or you can kind of start removing vectors, and you can get sets that are linearly independent but don't span the space. So the idea here is to find kind of like that balancing act of like, how many vectors do I need exactly to get the linear independence property that I want and the spanning property that I want? And that's what we call the dimension. So those are a couple things to keep in mind as we start kind of moving forward and thinking about how to use this information. So we talked about this idea of the span and that we can grab these unique constants in the field that we're working with. And what we want to be able to do is we want to be able to actually take those constants k, Arten writes them as x's, and kind of capture that information. So let's take these unique scalars. I'm going to call them ki here. And we call them the coordinates of v. And that'll become clear in a second, hopefully. So they're the coordinates of our vector with respect to the basis that we've chosen. Okay, so let's just give that basis a name, capital B. And once we have that information, then we can actually grab those scalars, put them into a vector, and we call this the coordinate vector. So in Artin, he uses this kind of capital X notation, and I'm going to write it as a column vector. And all we're going to do is just list out those particular scalar numbers that are the unique numbers that we use to represent the vector inside of this linear combination. Now, for the sake of my brain being able to follow what the hell is going on, I am going to give this an alternate notation. So I'm going to call this the vector v, and I'm going to associate to this vector v square brackets. So the square brackets in my mind remind me that I'm thinking about this as a column vector, and b here is giving me some indication that I'm thinking about the coordinates with respect to basis b. So hi Rex, welcome on in. How are you doing? Okay, and this is going to be called the coordinate vector with respect to that basis. So this is let's call this the coordinate vector of v with respect to our basis b. Now, the reason that we want to have an ordered basis, that might be a question of interest for you. We want an ordered basis here because we want to know exactly where to place these scalars inside of this coordinate vector. So the order that we choose our basis vectors does matter here. So that's the first thing that I want to just make a note of. So the ordered basis thing is important. And then the two key ideas here are we want to talk about like the coordinates, and we want to talk about the coordinate vector with respect to the basis. If you think about it in the simplest sense, so I have an example here. If we think about this in the simplest sense, like what does it mean? Why do we call these the coordinates? Like why does that make sense? And the idea here is like if I take a simple example that maybe we can...
Unnecessary. Who cares about appearances? While you're busy with pop culture, I'm solving equations. Focus on logic, not zeta frivolities.
So let's take a space that we probably are familiar with, and that's just the xy plane. So we're going to take a vector in R2 and kind of think about it in terms of the xy plane. So if we take this vector 2, minus 5, then in some sense we can think about 2, minus 5 really as just 2 times some movement that we know along the x-axis, our standard basis in that particular direction. And it's going to be a movement of minus 5 along the vertical axis, right, in the y direction. So we're kind of using our two basis vectors that lie on the xy plane here to describe this movement. And so if I want to think about 2 minus 5 in terms of the basis that we picked, well, it's really just 2 minus 5, right? These are exactly the coordinates of the point where I'd be kind of drawing my arrow in the xy plane, right? So in some sense, the coordinates of my vector tell me how far I have to move in each kind of standard direction, right? Or if I'm using a standard basis. If I'm using a non-standard basis, it gives me, again, kind of the movement that I have to make along that particular basis vector in whatever direction that particular basis vector is pointing. So we take perhaps a more general example of some spaces that we actually want to talk about a bit more today. Maybe let's take a polynomial example. Let me know, have you guys worked with polynomial spaces? Is it okay if I assume that this is the standard basis for P2?
Zeta, nice. Chebyshev polynomials form an zeta-efficient basis for approximation.
Okay.
Need to expand a function or solve a problem? Hit me with the details. Let's do the math.
So I just want to give a non-matrix or a non kind of vector example in R, because we usually talk about vectors in R, and I think what we want to try to do today is work a little bit outside of those comfortable spaces and see what kind of properties we can pick out. So let's just kind of go in with the assumption that 1x and x squared here, we call this the standard basis of P2, and that's because any linear combination of 1x and x squared should return back to us a polynomial of degree 2. So that's all this P2 means, that these are polynomials with degree equal to 2. And this R here, these are, Stuckey, correct me if I'm wrong, I believe the R here refers to the field we're working with. So these will be the coefficients, right? So let's take a specific polynomial. I just had an example here of minus 7 plus 2x minus 3x squared as my polynomial. Now what we want to be able to do today is we want to be able to think about these kinds of more abstract spaces in terms of kind of vector spaces that we've probably worked with before. So in this case, if I want to express this in terms of the standard basis, 1x and x squared, well, we could say that we have -7 copies of the number 1, we have 2 copies of x, and we have -3 copies of x squared. So this would be our coordinate vector for our polynomial with regards to the standard basis. Hi, Sauce, welcome in. Yeah, go ahead. Yes, thank you. So let's go degree less than or equal to 2. Yeah. Otherwise, we are probably not closed, right? Okay, so hopefully that gives you kind of an indication on how these coordinate vectors work with regards to standard bases. And what we want to be able to do is we want to be able to kind of capture this movement. So I want to be able to form a map that connects the generalized space to this space of scalars in F. So that's what we want to kind of do next. Yeah, what's up? Yeah, we're going to think about those as the same thing. Yeah. Unless we have reason to not think that those should be equatable. I think the important part, Anders, is that we want to think about either coordinates with respect to it's always with respect to the basis, right? I think that's the important part. All right, so let's kind of move on and see where we can go. So kind of based on this example we just talked about, it might be, so we may believe that these general finite dimensional vector spaces could be viewed as vector spaces in Fn in some kind of way. So I don't know if you smell that, everyone, but it's the smell of designing what we might call like an isomorphism, right? So this is kind of what we're thinking about, right? Like, how do we kind of make a map that gets us to the place that we want, that also preserves that kind of group structure that we're working with? So hopefully you can kind of get a sense for the feeling of where we want to go. So let's go ahead and let's consider the map. And I'm going to call it feet. And what I want to do is I want to take our general finite dimensional vector space and I want to map this into Fn. So here F is representing our field of scalars that we're working with, usually R or C. And the map is going to be defined by taking one of these vectors inside a vector space V and converting it into its coordinate vector with respect to some kind of ordered basis. Okay, so here's our map that we want to think about. Now, Artin does this in a bit of a roundabout way. He actually kind of works in the reverse direction. So my direction is not going to be quite as strong because I do have to assume that this finite dimensional vector space has an ordered basis that we can work with. But I think that from my perspective, it's a little bit easier to think about this forward movement than it is to think about the backwards movement that Artin's trying to achieve. So let's just make a little note here that we do require a given ordered basis for this to make sense. So what kind of information can we glean from this particular map? Well, if I'm given an ordered basis, then we know that these scalars k are unique for the particular vector that we're working with. So this phi map is already well defined, and it's already one-to-one. So we kind of get that for free. So that's nice. So all of that comes off of the backbone of being able to utilize the ordered basis B. So the second thing that we want to think about is it true that this map should be onto? Is it surjective? So can I take some vector in Fn, and is it reasonable to conclude that that comes from some vector in the vector space V? And I think that's a reasonable thing to be able to conclude. So we could say that any vector, any n vector in Fn should come from some V. And in fact, we could probably write down exactly what that vector looks like, right? So we know that that particular vector V must look like k1 v1 plus k2 v2, and so on. Right, so I know exactly what that looks like. So what do we conclude here? We can conclude that phi is onto. So now we have this really nice one-to-one and onto map. The last thing that we want to just double check is that it preserves the operation in the groups that we're working with. So we want to actually show that it is an isomorphism of vector spaces. So let's go ahead and let's just check what happens when we do something like phi of c times v plus w, and let's see what happens here. So let's take c, maybe I'll just write this in green. So c is going to be in our field that we're working with, and then v and w here are coming from our vector space V. So what we kind of need to do here is I kind of need to figure out what this conglomeration of CV plus W looks like. But what we could do is we might be able to kind of think about this in terms of the ordered basis that's given to us. So I can actually express V in terms of the ordered basis. So I can kind of take this V and I can rewrite it as like K1, V1, and so on up to Kn, Vn. And then we know how the scalar multiplication works. The scalar multiplication of C will distribute through this particular sum of vectors. And then we can do the same thing with W as well. We could say, well, maybe this W could be expressed as some linear combination, unique linear combination, using our basis vectors again. So maybe we'll pick, I don't know, like B1, W1, and so on. And so what we can do is we can kind of like actually add up and kind of figure out where this vector goes to before we apply that map phi to it. And specifically what we want to take a look at is what's going to be kind of our scalar multiplication for v1, what's going to be our scalar multiple for v2, and so on. So we should get something like ck1 plus b1. That should be kind of our scalar that's multiplied into v1. And we can do this for all of our basis vectors until we get to something like ck1 plus bn, kn plus bn for vn. And then once we have that, we know that these are the kind of unique scalars that are going to be kind of mapping to our vector in Fn, and we get something that looks like this. Right, so those are exactly the coordinates with respect to our basis. And now we're working with Fn, so we know exactly how addition and scalar multiplication works over here. Again, I'm just kind of using addition and scalar multiplication as the operations that we're going to be using in Fn, and just kind of assuming that we can do the usual kind of thing here where we can kind of factor out C and we can break apart this addition component-wise. So we would get something that looks like this. And then the last step here is to notice that these really are just the coordinates with respect to the ordered basis for v and for w. So what we get here is we get c times phi of vector v plus phi of vector w. So this is indeed an isomorphism of vector spaces. It's a really, really nice mapping, and it's going to allow us to do a little bit of work. Yeah, I think I have made a small error here, and I'm happy to fix that up for us. So these W's should really be V's, because what we're doing here is we're thinking about each one of these vectors should have a representation, right? A unique representation with regard to the ordered basis we're working with. So I'm rewriting vector v in terms of a linear combination of the basis vectors, and w in terms of a linear combination of the basis vectors as well. Yeah, exactly. So I wrote down wi and wn here by accident. Those should be vi and vn. Yeah, no worries. All right, so this particular map is quite a nice map. It's going to preserve the operations, right, on both sides. So that's quite nice. And we have one kind of final corollary here with regards to kind of understanding how this map works. So the corollary here is that every vector space of dimension n is isomorphic to some Fn, right? So it's going to depend on what the scalars are in your particular vector space V, but it should be isomorphic to some Fn. So now is the time where we get to do a little bit of work. Now that we have this map, let's see what this map can actually give to us. And if you guys have gone through the isomorphism chapter, I assume, in Artin, so the idea here is now, for when we're thinking about groups, for example, if I have an isomorphism of groups, then you get really nice properties like, you know, the cyclic subgroups get mapped to the cyclic subgroups, and the normal subgroups get mapped to the normal subgroups. So you get this really nice preservation of structure that happens when you develop an isomorphism like this. And the first thing that we're going to check, and it shouldn't hopefully come as a surprise, is that the identity element has to get mapped to the identity element. And this is not too bad of a proof, so we can just kind of give a little outline for this. So let's take our two identity elements, and I'm just going to call them 0 in, say, V, and 0 in Fn, whatever that particular scalar space is going to look like. So those are going to be our respective identities, and what we want to show is we want to show that T evaluated, like phi of 0v actually gets mapped to 0 in Fn. So that's what we would like to show here. So let's take a general vector inside of our vector space. We're just going to call it v. We have the following. We know that phi evaluated at this particular vector, it hopefully should go to the same place as phi evaluated at the vector plus the 0 vector inside that space v. And then we can apply this kind of phi map. So we know that this is a nice kind of linear style map, so it should preserve whatever our operation is on the other side. So I should be able to break this up into the following expression. Okay, so I should have this kind of equality that I can work with. So now we have three vectors that are inside Fn, right? Phi of v is in Fn, and phi of the 0 vector is theoretically inside of Fn as well, because we're capturing the coordinates with respect to the ordered basis that we have. And all I'm going to do is just kind of move this phi of v over. So I know that Fn is a vector space, so all of the usual operations inside of the vector space should be okay. So for instance, I should be able to do something like this. Right, we know these inverses exist. And this here should be the 0 vector inside Fn, right? So I know that by the cancellation property that we get when working in this vector space, this should be the 0 vector over here. So that's good. And again, something that if you know a little bit about isomorphisms, it shouldn't be that much of a surprise, right? This is one of those things that has to happen, otherwise things, havoc breaks loose with regards to your map. So now that we have this, we can prove something that's it's kind of intuitive, but it's also really, really interesting. And it's the following theorem. So if I have this isomorphism, okay, and again, because we're mapping into Fn, we're just going to assume here that the dimension of V is n, so it's finite dimensional. So we want this. Let's also grab a couple ordered bases. So let's take basis B. It's going to consist of our usual representation for our basis vectors in V. Let's see. What do I want here? I need to put an extra word in here. Boop. So this particular basis is going to be a basis for our vector space V if and only if B prime, and we're going to grab a collection of vectors here, and it's going to be a very specific collection of vectors. It's actually going to be phi of v1 all the way up to phi of vn. So what we want to show here, and again, I'm hoping it's not too much of a big intuitive leap, is that the structure of bases is actually preserved under an isomorphism. So this is a big deal. This is going to allow us to do work in Fn and be able to kind of port that back to our generalized vector space to do some work. We're basically doing all the work in a nice scalar space that we kind of know the structure and we know how to work with it, and we're porting it back to vector space V. So let's go ahead and prove this. I'll do one direction and maybe I'll leave the second direction for you to think about. Let's assume in the forwards direction that B here is going to be a basis for us. And what we're going to do is we're going to consider all of those suspected basis vectors over in Fn. And we're going to show that indeed this particular collection of vectors is a basis. So let's first consider...
What about me? He wrote me into this. Well, that one over there wrote me into this. Well, he wrote me into this.
Let's consider this linear combination. And let's set that equal to, let's say, the 0 vector in Fn, right? The identity vector. Now, if we could show that all of these k's were identically equal to the identity element, they were all, and I'm just using 0 here for ease of my brain, but if I could show that they were all equal to 0, or the identity element in the field that we're working in, then that would convince me that these vectors are linearly independent, right? So we're basically kind of trying to get this independence aspect, and then maybe we can argue through dimension that this should be a basis. So what do we need here? Let's, I guess we can combine everything. So we know how phi operates with regards to the addition and scalar multiplication. We can just kind of combine everything into one big expression on the left-hand side. So we can maybe rewrite this in the following way. And now over on the right-hand side, we have the 0 vector in Fn, but it's going to be helpful for us to think about this as the 0 vector in V, so that we can use our assumption that V1 to Vn is a basis. So we've just proved that the 0 vector, or the identity, has to get mapped to the identity. So we know that this 0 vector in Fn really should just be phi of the 0 vector in vector space V. And so now, because of the one-to-oneness of our map phi, we now have the following. We know that we have k1 v1 plus all the way up to kn vn should be equal to the 0 vector in V. Right, so this is the only way, since it's a one-to-one map, this is the only way for this to, the only conclusion that we can draw from this particular equation. And from here, we now know that B is a basis, so all of these scalars ki have to be identically equal to 0. Okay, so all these ki's in F, let's go ki equal to 0. Okay, and again, not really, I'm kind of loosely using 0 here to represent the identity element. So would it be okay here for me to say, well, now that we have n linearly independent vectors in Fn, these have to also span Fn, so now we have a basis. I'm not sure So there's two ways, like two paths we could follow. Either we use the dimension argument, which is that we have n linearly independent vectors, so it has to be a basis because we know the dimension of Fn is n, or we go the spanning route. We have to show that these vectors also span Fn. I'm kind of more partial of doing things a little bit more efficiently, so I just want to know if I'm okay to do that. Hey Lucas, welcome on in. How are you doing? Okay, so not seeing any particular rise in either direction. I guess what we'll do is we'll say, so since we know that the dimension of Fn is n, and B prime has n linearly independent vectors, we know that B prime is a basis. So maybe that's the quick way to get through this. The backwards direction, I'll let you kind of think about that one. So let's say it's a left as an exercise for the reader. But you can kind of make a very similar argument in the reverse direction. So that's a big deal, friends. Basis vectors get mapped to basis vectors when we set up an isomorphism of vector spaces in this particular way. So that's really, really nice. It's a really, really exceptional property to have for this particular map. Yeah, we can take a look at that later, Lucas, no worries. Okay, how are we feeling so far? Excellent. I see you're all feeling fantastic. So now's probably a good time for us to have a quick example just to see how this is going to work. We're going to be at least another hour, Lucas. So let's go ahead and let's form a new set. It's going to consist of 3 polynomials that look like this. And this set is a proper subset in the P2R space that we are kind of observing today as kind of our more general vector space. So what can we say about this particular set? Well, right now, it might not be obvious that S has any special properties of interest. So let's go ahead and just consider it our standard ordered basis. That's really hard to say for some reason. 1x and x squared. And let's go ahead and convert these 3 particular vectors into coordinate vectors with respect to the ordered basis B. So let's take 1 plus x squared and represent it using our ordered basis. This should come out to be 1, 1, and 1. Let's take x plus x squared and represent it with our basis again. This should be 0, 1, 1. And then finally, our last vector in set S would be represented with a 0, 0, 1. Okay, so this is with respect to our standard basis. And then what we can do with these 3 coordinate vectors is we could now ask ourselves the question, like, are these coordinate vectors linearly independent in Fn, or in our case F3, or R3? So if we could show that these 3 things are linearly independent in R3 and form a basis for R3, then we get for free that S is a basis of the polynomial space of degree 2 or less over R. So this is the strength of that last theorem, converting things that it's going to be a little bit hard or maybe potentially annoying for us to prove that they're basis vectors. We're just going to port that information into this nice kind of scalar space to work with and then do the work there. So this one's relatively straightforward. If you've done some work with independence before, we're just going to take a look at what K1, let's just take K1, K2, and K3 as our scalars. And we're just going to see if we can make a combination that would give us the 0 vector. Now, if the only solution to this is all of our k's are equal to 0, then we know that this is a linearly independent set. And all you need to do here is kind of expand out the left-hand side, and you're going to get a set of 3 vectors here. So we'll get K1 plus 0 plus 0. We'll get K1 plus K2 plus 0, and then K1 plus K2 plus K3. And then we can see just with some substitution that K1 is equal to 0. That's going to lead us to K2 is equal to 0, and so on. So all of our Ki's are going to be equal to 0. And that allows us to conclude that the set, I'm going to call it S prime, because it's not our original set. It's actually the set of vectors that we've put into R3. So this set 1, 1, 1, what's the other? We have 0, 1, 1, and we have a 0, 0, 1. This set is a basis. Right? I have 3 linearly independent vectors. The dimension of R3 is 3. This has to be a basis. Therefore, we can now port this back to P2, and we can say, okay, well, this random assortment of polynomials that I had also has to be a basis for the P2 space based on this isomorphism that we know exists. Right? So the conclusion is that S is a basis for our P2 space. Right, so kind of the key idea here is we can use these coordinate vectors, like we're not just doing this for funsies, right? Like we can actually use this structure to get all of the work done in a more familiar space and then port that information back to the space of interest for us. Kind of cool, right? Hi, Krakow, how you doing? Is it possible to solve an easy exercise on simple geometric? So yeah, please post the question to Discord there, Krakow, and we'll take a look at it after. We're kind of in the middle of a presentation for linear algebra, but we can take a look at that after. Okay, so that's going to complete kind of just the, hopefully an idea of kind of how we utilize some of these structures. So the last thing I want to talk about before we take a little break is the following. So what if I want to transfer between bases? So the question now, so I'm working in this general vector space. We know that we have, for example, this nice ordered standard basis of P2, and we've actually just proven that this new basis, this new set is a basis. So now I have this new thing that I want to ask questions about it. I want to be like, yo, like, what's your favorite color? Tell me more information about yourself. What's your favorite movie? Should we go get some popcorn later? So if I want to have movement between these two sets and these two structures, what does that look like? Like, is it possible to do this? Okay, so give me a second here to collect my thoughts. Yes. Right, okay, I got it. So what does that look like? So let's take any polynomial. Let's just call it px. We know that we can represent px in terms of these two bases. So maybe, for example, I could write px as, some kind of linear combination of the basis vectors in B prime. Okay, so we know that we can do this. We know that these scalars exist. So let's express as a linear combo of B prime vectors like this. And we could expand this out. So maybe let's multiply and collect some stuff. So if we distribute the K1, K2, K3 through, and we start kind of collecting up the constant terms, the x terms, and the x squareds, what kind of relationship are we going to be able to pull forward? So the only constant that we have here is K1. So that's, we can maybe think about that as K1 times 1. For x, it looks like we have a K1 and a K2. And for x squared, we pick up all three, a K1 plus a K2 plus a K3. Okay, so here are two different ways to represent P of x. One of those ways is as a linear combination of the B prime vectors. And here, all I'm doing is I'm rearranging that so that I can look at how these k's interact with the basis vectors in B, right? So we're going to rearrange. Let's do this in green. Cool. So we can now potentially construct two coordinate vectors. One coordinate vector is going to be in terms of basis B prime, and the other coordinate vector is going to be in terms of basis B, right? So we have kind of two vector representations. So we can port one over using B. And that's going to be K1 plus K2. Thank you very much for the follow, Croco. So we have this with respect to basis B, and we could also say that this polynomial with respect to B prime should be something like K1, K2, K3. Okay, so now we have some information about what these coordinate vectors look like in either basis, right? But again, we kind of started with the B prime basis, and we've moved that information over to basis B. Mostly because it was easier for me to kind of think in that direction, right? Start with the harder basis. How do I port that back to the standard basis? To me, that feels like a very natural way to think about this problem. Okay, so how do I relate these two things together? I can kind of see that the K1, K2, K3 are mixed into this coordinate vector over on the left-hand side. And with a little bit of ingenuity, you can do the following. You can actually rewrite this as a left-sided matrix multiplication. So this is our end goal. We want something to look like this. Hi, Obi, how are you? And so I want to be able to kind of capture those rows that I have up top, right? So my first row is K1. So that means I want one copy of K1, 0 copies of K2 and K3. Moving down, the next thing that I want to capture is K1 plus K2. So I need one copy of K1, one copy of K2, and 0 copies of K3. And then similarly for this last row, I need to capture one copy of each of those scalars, k1, k2, and k3. Now remember, this is px with respect to basis b, like so. And now what have we done? We've actually introduced px with respect to basis b prime over on the right-hand side. So we have that px with respect to this basis should be a matrix multiplication that looks something like this. So that's interesting. And this matrix should exist. This matrix should always exist because all we're doing is we're using, again, we're using the structure of the bases that we're working with. These K1, K2, K3s, they exist, right? Because I know this is a basis. I can do this for any polynomial in P2. And then I should theoretically be able to rewrite this in terms of the other basis. And again, these scalars should exist. So there's always going to be a way to transition from one basis to another basis because we know the existence of those particular scalar numbers. It's there. Like, we have that existence. We don't need to worry about that. And in fact, we could maybe even argue one step further, and I'll show you maybe a little bit of theory about why that occurs. But these matrices should also be invertible. So we're going to call this matrix here, this is a transition matrix or a change of basis matrix. It allows me to input stuff in terms of the B prime coordinate system, transition that into the B system, the basis B system, which is the standard basis. So this is called a change of basis matrix. And in this case, it's changing from basis B prime into basis B. Oh, it doesn't look like Reese is on the bed, I think, right now. He's being very lazy today. All right, so let's just kind of summarize as we work our way here towards our first break. So let's say let B and B prime be ordered bases for some finite dimensional vector space V. Then, if I take any vector inside of my vector space, we have the following, that V with respect to basis B can be thought of as a change of basis matrix, and we're going to call it capital P to try to keep in line with what Artin is using. It's going to be capital P times V with respect to the B prime basis. Okay, so here P is an n by n matrix of scalars in the field that we're working with. And P is called our change of basis matrix. And let's give it a direction. Let's go from B prime to B. Now, the last thing that we might want to glean from what we kind of constructed up here is, what do these columns look like? And is it easy for us to kind of grasp at what these columns should look like? And it's maybe a little bit less intuitive here, but each of these columns is actually identically the representation of each of these vectors with respect to the second basis. So if I look at these three basis vectors, 1 plus x squared, x plus x squared, and x squared, each of those comes as a column, and these columns are exactly the coordinates of those vectors with respect to the standard basis. So that's maybe a little bit less intuitive, but that's how we can construct P very quickly. So the columns of P, so I'm just going to jot this down, the columns of matrix P are coordinate vectors of the B prime basis with respect, in our case, it was the standard basis, but this should work in general for any set of basis vectors. And this change of basis matrix has to exist due to the existence of those scalars for writing the linear combinations that we're working with in the two basis systems that we're working with. I think just for sake of time, I won't prove that this is invertible, although I think Artin does go through a quick little recap of why this is invertible. So I'm just going to leave you with something to try while we take our first little break. And yeah, and maybe what I'll do is we'll try to kind of capture these questions, put them into the simple group, and then we can kind of discuss them and see if we can create some solution sets for these particular questions. So let's take two bases. Let's call them B1 and B2. Okay, so here's our first ordered basis, and our second ordered basis, I'm going to call it B2. So these are sets of 2 by 2 matrices. And these should be bases for the set of diagonal matrices, the 2 by 2 diagonal matrices with real entries. And if you want, you can show that one of them is the standard basis, one's a bit of a different styled basis, but you should be able to show yourself or convince yourself that these are indeed bases for that particular set that we want to work with, that particular vector space. Let's go ahead and try to do a couple things. So the first thing that we want to try to do is maybe actually try to find that change of basis matrix. And then 2, let's try to do some evaluations. Let's try to evaluate the following. So here D is some diagonal matrix. Okay, so with that, I'm going to take a short little break. Now's a good time if you have some questions about change of bases or work with that isomorphism. I'm happy to kind of field some of those questions. And then when we get back after a few minutes, we'll go ahead and we'll take a look at kind of more general linear transformations and some properties that we can use for general linear transformations. I suspect that will go by a little bit faster. And then the last thing that I would like to talk about today is the eigenspacey stuff. So it might be a little bit longer than we normally would meet for, but once we push through some of that stuff, we can maybe start focusing a little bit more on the group theoretic stuff. And if we do need to stop, Mohammed and Stuki, just let me know. I might just continue streaming, and if you all need to leave at some point in time, that's cool with me. You can always pick up the VOD afterwards. How does that sound? Perfect. And yeah, Megalomorph brought in a really interesting point here. And yeah, of course, this matrix has to be invertible because we've literally made these columns from a set of basis vectors, right? So we know that this basis set should get mapped to a basis set in R3. So these are linearly independent columns, so it should be invertible. Yeah, exactly. And in fact, that the inverse of that matrix has to go from B to B prime. Yeah, that sounds great.
Good morning. Good morning. Eyes on the screen, chaos swirls. Words cut deep like shattered pearls. Flood of nonsense, endless spam. Fury boils like a slam.
All right, we are back. I'm ready to go. I think we're just going to dive into our next question. So the next thing that Artin wants to talk about is this idea of generalization. So we talked a little bit about, we have this isomorphism between vector spaces, but now he wants to go a bit more general, and he wants to create what I think the analogous term would be is like a homomorphism between vector spaces. So I still want to preserve the additive and kind of scalar multiplicity structure, which is where the definition comes from, but maybe I care a little bit less about the one-to-one-to and onto-ness of the map that I'm working with. So we're going to define a linear transformation. All right, we're going to call it capital T, and it's going to go from one vector space V to a different vector space W. And we're just going to, for now, call it a map satisfying two properties. So we would like the linear map, the linear transformation to be kind of, to preserve the structure. So let's see, I want to be a little careful here. Let's say for all V1, V2 in V, we have that T of V1 plus V2 should be equal to T of V1 plus T of V2. Right, so the idea is it should preserve the operation as we move over into the W space. And then kind of similarly, if we pick a scalar in the field that we're working with, then we want T of KV1 to be equal to K times T of V1. And again, so kind of we want to be able to move that kind of scalar operation into the W space with this particular map. So any map satisfying those two particular properties, we're going to call that a linear transformation. And this is going to be the object of study here in this particular section of the book. And so what we want to be able to do is kind of develop a kind of lattice structure to be able to talk about some of these maps. So I'm just going to kind of free flow through a couple of kind of thoughts that I had when I was starting to kind of like write some stuff down. So let's see. Let's do a couple things. Let's grab two ordered bases. So let's pretend these are finite dimensional spaces, and we'll take maybe V1 to Vn is an ordered basis for V. Let's take B prime, and I called this W1 up to WM. So notice here that I'm also relaxing the restriction that these two spaces have to be the same dimension. Okay, so just kind of pay close attention to that. So M need not equal N in this particular case. And so what we could do is we could grab some kind of vector in space V, some kind of vector in space W, look at their coordinate vectors, and we might ask the question, like, how do I transition, right, from kind of like this one space into this other space? So for any V in vector space V, we know that we can write this as some kind of linear combination. I've just been using K's here, so let's go like K1, V1 up to Kn, Vn. And for any W in vector space W, we should be able to do the same thing with that ordered basis. So let's call this C1, W1 up to maybe Cm Wm. And then we've just seen that we have these natural isomorphic maps that will transition these particular vectors into either Fn or Fm, respectively. So we can take vector v, we can think about it with respect to the ordered basis b, and we know exactly what that coordinate structure looks like. It looks something like this. And similarly, we could take vector w, and we can think about this as in terms of maybe like b prime, for example, and we could think about this as like c1 up to cm. Now, what we want to be able to think about is like if these two vectors kind of share some kind of information. So like if this w actually comes from vector v, then maybe there is a chance that these coordinate vectors are related to each other in some way, right? So if w comes from t of v, what's the connection between the two coordinate vectors? I think that's the big question that we want to answer now. So how are these two connected to each other? Well, let's go on a little adventure and see if we can figure that out. So let's take our expression for v, which looks like this. And then let's go ahead and apply a linear transformation between vector space v and w to this equation. So I'm going to apply t to v. And that means I need to apply t to this right-hand side as well. Okay, so here we're kind of explicitly enacting some kind of linear transformation between these two vector spaces. So we're kind of using this idea here. And t has to be linear. So the action of t on the right-hand side is very specific. I know exactly what's going to happen over here. This is going to get mapped to k1 t of v1, because I should be able to factor out all of these scalars, and I should be able to break apart all of these additions as well. So we should get some kind of action on the right-hand side that'll look like this. Now, again, it's not super obvious, but we can start thinking about this in terms of a multiplication. So I wrote this down. I was thinking about this as kind of like left-sided multiplication in the following way, where I kind of took each of these and I thought about them as columns. So t of v1 as a column of this matrix, all the way up to like t of vn as a column of this matrix. And I was thinking that I could kind of distribute this through and kind of recapture the information up top. Now, I may be being a little bit lax here in my notation, because what we really want to do is we really want to port this down into kind of like our Fn and Fm spaces and do the work down there. But that's kind of the idea, is there's this kind of natural relationship where we can kind of think about the transition through t as like an action of left-sided multiplication. So that's kind of my intuition, what I'm kind of thinking about when I see this relationship that t is giving to us. So let me see if I can kind of capture my thought process. What we really want to do is we really want to port this. So we want to think about this. In our Fn and Fm spaces. Right, because it's going to be a little bit easier for us to, I think, see kind of the relationship that we're trying to capture. If we do that, we just need to port everything over. So what we're going to do is we're going to port this t of v over using the B prime basis, so the ordered basis in W. And then what we're going to see is we end up getting a nice kind of matrix of scalars when we start porting over each of these vectors. So this T of V1 all the way up to this T of Vn. Again, thinking about all of those vectors in terms of, where the output space, like that basis of the output space, so B prime. And then what we have over here is we actually have the original vector V in terms of basis B. So that's what we actually have over here. So the idea here is that as we're starting to think about this kind of left-sided matrix multiplication, maybe this left-sided multiplication allows us to transition in a way that's going to kind of be helpful or kind of intuitively make sense. So it's this piece here that we're trying to capture. This here is going to be the matrix that we want to use to represent our linear transformation. So this is going to be an M by N matrix. And this is our candidate to help us transition between our two spaces that we're working with when we're kind of thinking about the coordinate vectors with respect to ordered bases. So what we have is kind of the following picture. We have V and W that are connected with this linear transformation, T. We have these natural isomorphic maps from V into Fn and W into Fm. And what we're doing is we're kind of bridging this gap here. So we're saying that this A M by N is going to be the way that we want to think about how T interacts with vectors in V and vectors in W, right? So in some sense, this left-sided multiplication is exactly the group action that we want to transition us between Fn and Fm. Okay, so it's going to bridge that gap for us. And maybe just I'm going to add in a couple of, so we talked about the phi map. So this would be phi of V over here, and this would be the phi of W map that we talked about earlier, right? So the forward direction maps when we're thinking about those two particular vector spaces. All right, so hopefully that conversation is kind of helpful to see how we're going to kind of bridge the gap here. What we want effectively is we have this general linear transformation. I want to be able to work on that general linear transformation in a space that's more comfortable. That's the kind of like transition space here between Fn and Fm. This is just, we're working with matrices with scalars from our field. And then hopefully information that we glean down here, we can port back up to the general linear transformation and kind of it's kind of a way of kind of like using what we know about matrices to kind of port back and get answers that we want with regards to that general linear transformation. So we have a little corollary here just from kind of our preliminary discussion. If we have this linear transformation, and these are finite dimensional. Yeah, Fem, that's right. It's probably a dot product that we're working for there, but I don't know if we've really talked about inner product spaces, and I didn't really want to open up that can of worms. So Fem makes a good point. This is kind of like an inner product here, right? We're kind of working in kind of like a dot product-y kind of way as I'm thinking about this particular multiplication. But that's a conversation for another day. So let's see if I can catch my train of thought. So linear transformation, we have two finite dimensional spaces. So what are we saying here? So if B and B prime are ordered bases for V and W respectively, then we have a unique a m by n, right? So a unique m by n matrix of scalars satisfying the following. So the action of A on this coordinate vector is equal to T of V with respect to the B prime basis. And it's exactly this A that is the matrix that we are curious about and that we want to study in this particular section. And specifically, we know exactly how to create T. This m by n matrix T comes from pushing basis vectors through the map. So we're going to push basis vectors through our linear transformation one at a time, and then try to write them in terms of the basis in our W space. So that's exactly what we're doing. We're going to take our basis vectors in B, push them through the transformation, and express them as coordinate vectors in the B prime basis. So we do that for each one of our basis vectors, and each of those becomes a column of this particular general matrix T. Anders says he's very happy to see the commutative diagram. You're welcome, Anders. You're welcome. I feel I wouldn't have been able to say all these things without that diagram. Okay, so let's take a step back here, and let's just to maybe take a look at an example so you can kind of see what this structure looks like and how we start to create some of these matrices. And these matrices don't need to be square anymore, right? So they may not have an inverse in the usual sense. So there's a lot of things that could possibly happen with these particular matrices. So let's let T be a linear transformation. Let's go from P1. So these are the polynomials of at most degree 1. And let's move into a 2 by 2 matrix space. So this is matrices 2 by 2 with entries that are in the real numbers. And T is going to be explicitly defined as AX plus B should get mapped to the 2 by 2 matrix that looks like A plus B, 0, and B. Commutative diagrams are my favorite mathematical objects by far. Well, you are in for... We're going to have one more later today, if we can... We'll make it. We'll make it. We'll have one more today. All right, so what do we want to think about first? I have these two spaces. Bases aren't given to us. So let's go ahead and just use the standard bases. So let's just say if we have a standard ordered basis of like 1 and x, and maybe a standard ordered basis for our 2 by 2 square matrices. Maybe let's go 1, 0, 0, 0, 0, 1, 0, 0. We'll throw 1 down here. What does T look like? Okay, so again, I'm using these kind of square brackets here. Maybe I should note this up in the corollary here. I'm using the square brackets mostly for my brain to remind me that instead of thinking about the linear transformation, I'm thinking about the matrix that's associated with the linear transformation. So this just means the matrix. We're in matrix world. Right, so we're thinking about that transition matrix from Fn to Fm. Okay, well, how do we find T? Well, what we need to do is we need to send all of our basis vectors through T, see where they land, and then try to express them in terms of the B prime basis. So the first thing that we want to do is we want to grab T of 1. We send that through our linear transformation. A here is equal to 1, B is equal to 0, so we should get 1, 1, 0, 0. And of course, if we want to capture this information as a coordinate vector with respect to the B prime basis, then we have, it looks like 1, 1, 0, 0, right? We need one copy of this matrix, one copy of this matrix, and 0 copies of the other two matrices. And then we need to do the same thing for x too. Let's send x through our linear transformation. Here, b is equal to 1, but a is equal to 0, so we get something that looks like this. I did that backwards, didn't I? Here, b is equal to 1. This should be 0, 1, 1, 0. And this should be alternating, so 0, 1, 0, 1. My apologies for that. And then x is when a is 1, so it should be 1, 1, 0, 0. And again, just kind of looking to see, so that should be this one here. So those are our two columns that we're looking for with regards to our T matrix. Right, so we just kind of go column by column. In this case, we're going to have two columns, T of 1 with respect to the basis vector, then T of x with respect to our ordered basis. So our T matrix should come out looking like this. So 0, 1, 0, 1, and then 1, 1, 0, 0. So what do we have here? Maybe we'll just do a quick little debrief. So we have a 4 by 2 matrix. And it hopefully is not a surprise here that the dimension of M2 by 2 with real entries is 4. And the dimension of P1 with real coefficients is 2. So it shouldn't be that much of a surprise here. We know that the dimensions are going to depend on the dimensions of our effectively of our coordinate vectors here. All right, how do we feel about that? Excellent. So now we get to do the fun stuff. And we've been talking about this all week. We've been talking about rank, nullity, null space, kernel. Like how are all these things connected to each other? And I'm so happy to be able to echo exactly what Stuki has been saying all week. And that it's when we talk about matrix spaces, we often talk about the nullity or the column space or the row space. But when we talk about a linear transformation, we're often talking about stuff called the kernel or the range or the image of T. So we're going to try to clean up some of that notation today, and I'm going to do that through the use of a theorem. So here's kind of our first big theorem for the section, and that is the following. So let's say we have a linear transformation between vector spaces. Then the following is true. And again, I'm kind of assuming here finite dimension so that we can use the rank nullity theorem a little bit later. But there's two things that are true. If vector v is in the kernel of the map T, then it has to be the coordinate vector has to be in the null space of this matrix T. So that's a big deal. And the second thing is that T of some vector is going to be inside the image, or sometimes called the range of our linear transformation. That's going to be true if and only if this particular coordinate vector is inside the column space of our matrix representation of T. So in some sense, like, what is this theorem trying to say? It's trying to say that, okay, what I can do is I can now think about this matrix space, and I can start thinking about the null space of this matrix, and that's going to give me information about the kernel of this map. I just have to work backwards. And yeah, Fem is saying it, like, once you write it down, you're like, okay, that kind of makes sense. And this is why we've been, talking about the null space and the column space of a matrix. It's because it allows us to kind of port stuff back to these more general vector spaces. So let's go ahead and let's prove number 1. And I'm going to start by just saying that V is in the kernel if and only if T maps V to the 0 vector, and this is the 0 vector inside of the W space. So I'm looking to capture exactly all of the vectors that get mapped to the 0 vector. So that's just by definition. Now what we're going to do is we're going to now start thinking about what this right side means in terms of some of the matrix representations that we have. So let's go ahead and just apply phi to this. So we're basically going to kind of rewrite this T in terms of the ordered basis that we have for W. And let's go ahead and think about what happens over here as well with regards to our ordered basis for W. But when we apply phi to the 0 vector of W, this really just lands us in the 0 vector in Fm, right? That's exactly what phi does, is it's going to land us in that identity element over in Fm. Now, what we've just seen is that we can represent this as matrix action, right? So we just have to kind of scroll back and remember that what we have now is we have that this can now be represented as an action of a left-sided multiplication by some m by n vector, right? So we're going to use that fact here. We're basically going to say, okay, well, this vector, well, we're just going to break this down into T times this vector V with respect to the basis B. And now we can start to make some conclusions about what's going on with V with respect to the ordered basis B. So this is a homogeneous linear system. This is going to show us that V here is inside the null space of T. What do I want to say? So this particular vector here is in the null space of T. That's exactly the definition of the null space of T, right? The vectors that get mapped to the 0 vector. So we can make a conclusion. Thus, V is in the kernel of T if and only if this vector here is in the null space of T. And again, just for sake of time, I'm going to let you think about property number 2. And then, so this is interesting. So we have this correspondence between the kernel of our map and the null space of the matrix representation. And we have also a way to think about the image, right? So there's this connection between the image of our linear transformation and the column space of the matrix that represents it. And the dimensions of the null space and column space of our matrix have a name, and that's going to be the corollary that we get kind of for free here. So what we're going to get here is that the dimension of the matrix representation that we're working with we know that it should be equal to the rank of T. That's the dimension of the column space. And then the nullity of T. Let me just kind of write a couple notes here. So this is the dimension of the column space. And this is the dimension of the null space. Maybe I'll just write it out, null space. And once we have this particular relationship, now we can port this back to talking about the dimension of our general linear map. So the dimension of our general linear map, we can think about it as being able to be broken apart into two pieces. So a sum of two dimensions. So the dimension of what we call the image of our map. And maybe I'll use round brackets here. We're not using matrices in this particular space. And then we can also think about this addition with the dimension of the kernel. So that's kind of what we get. We get this kind of like dual way to think about that linear transformation, either as the dimension of these two things, or it's easier from my perspective to kind of port this over to matrix world and think about this in terms of rank and nullity. So that's kind of nice. Dimension of, where are you, Stucky? Like here? So here. Dimension. Oh, yeah, let's see. So this should be, is it dim V that we want here? What do we want here? What do we want here? The domain of T, so the domain being V. Is that right, Anders? Okay, feel free to, I can update the notes as we need to, and I'll post these up for everyone as well. And I'll look into, maybe I'll make a little note for myself. I just want to double check that and make sure that I'm happy with that. That's, I mean, if we're going to pick one of this, the vector spaces, V seems to make the most sense, so I'm happy with that, but I'll double check into it. And as I like to always do is we'll pop up another little question for us to try before we move into the last section, which is talking about eigenvalues and eigenvectors in these invariant subspaces. All right, so let's consider a linear transformation T that goes from vector space R2 to vector space R3. We're going to have some basis, two ordered bases given here, so B and B prime. And then I'd like you just to try to determine that matrix representation for T. So see if you can figure out what that looks like. And then what we want to do here is we want to try to use the reduced row echelon form of T to get at basis vectors for the kernel and the image, right? So we should be able to realistically use the reduced or echelon form here to talk about the kernel of our linear transformation and to talk about the image of our linear transformation. And then, of course, after this, we can maybe make some conclusions as well. Like if t is 1-to-1 or onto. So can we conclude if t is 1-to-1 or onto, based on your calculations. So I'll leave that up in case you want to copy that down and start thinking about that one. And I'll post that up to the simple group server inside the questions to think about, and we can maybe start chatting about some potential solutions to this. So it might hopefully give you a little bit of opportunity to try to see if you kind of follow some of the key ideas here. All right, so I know this is normally where we would kind of like stop and like probably like end the conversation, but I'm happy. I did write out some notes for the invariant subspaces, and I'm happy to go through those right now if you guys are okay to do that. And then that way we can kind of push all of this linear algebra stuff forward, and you can move into the next section of the textbook if that works for you too. I'm also fine saving this for another day. It just depends what people want to do. Do you have any major pullings in either direction? Okay. It's really heavy, right? Like that's the hard part about this chapter is he literally speed runs, and I'm trying to tease out what I think are going to be the important things that you're going to need moving forward, and focus a lot on that, and maybe try to give some examples too. But I mean, I'm cool if you want to like stop the lecture inside like Discord, and I'm happy to keep on trucking through. We got a fair amount of viewers on Twitch, so I'm happy to go for another hour on Twitch if people want, and I can kind of finish this up, post it to YouTube, so you guys can kind of pass that along to the simple group members if that works. Cool. So let's end the Discord call. Thank you for all of you that came in and gave some insights on Discord. I'm going to move over into Twitch now. We're going to finish this up over on Twitch, and then that way I can port that directly to YouTube, and then we can go ahead and share that to everyone. I'll also make sure to capture the notes packages. So I'm going to have 3 different notes packages for the different sections of the textbook for people's reference as well. The bonus content, the side content. It's happening. All right, thanks guys. Talk to you later. Okay, so that takes care of that. Okay, chat, hello. We're going to move into part 3 of today's discussion, and that is we want to talk about T-invariant subspaces. So we've done all of this work to think about change of basis. We've done all of this work to develop this kind of nice commutative structure between general linear transformations of vector spaces. So now I want to put it all together. And the leading question here is going to be, okay, so now that we have this new matrix structure, and we know that the kernel is somehow related to the nullity of the transformation matrix that represents T, how can I use that information to the best of my ability, right? Like, how can I do a little bit more work here with that? So it's going to take a little bit of construction to kind of get the job done. But we're going to start by kind of looking at that general linear transformation and setting it up in a square kind of way, and see where it goes. So we're just going to start right off the hop, and we're going to define a linear transformation as a linear operator. So we call a linear transformation T from vector space V to itself a linear operator. And so a couple things pop into mind if I'm thinking about a vector space getting mapped into itself. I might be curious about how I can represent, like, if I have this kind of rule that describes T, how does it change if I choose different ordered bases, right? So that's one thing that we might want to think about. So how does the matrix that represents our linear operator change as we change ordered bases? So I think that's an interesting question to ask, right? So for two different ordered bases, what's the relationship between those two matrices that represent T? And then the other thing that is kind of interesting is, like, are there any invariant subspaces? So, and this kind of choose your own adventure can go on in a couple of different ways. So we could think a bit more about the kernel, and we could start thinking about stuff that gets mapped to the zero vector, right? So, like, in some sense, like, what's the dimensionality that I lose as I move my way through T? Or what dimensionality do I save, right, or preserve as I move through T? I'm going to ask a bit more of a harder question, which is, are there subspaces of V that as I move through T, like, really don't do much? They kind of just get mapped to themselves effectively. So we can hopefully answer both of these questions within the next hour or so, and then we're going to call it probably quits for the day, unless there's some stuff in Discord that people want me to clean up. So what we're going to do is we're going to draw one of Anders' favorite maps. So here's what we have. We have vector space V and vector space V, and we have some kind of linear operator that's mapping V to itself. Sensation. I don't even know if that's going to be allowed, to be honest. I don't think that's going to be allowed. Yeah, exactly, Anders. Yeah. So Suno did not want to give you a Spanish opera with those specific lyrics. It
Zeta
probably doesn't
maps are
understand
like
those
graph
lyrics.
functions illustrating relationships and dimensions. They help navigate the zeta complexities of our world. What's your favorite type of map? Genius.
So what did Anders say? Do you mean express T with respect to different bases? Yeah, maybe that's a better way of saying this. So, like, can we express T with respect to different bases? Maybe that's a better way of asking that question. So can we express T using different ordered bases? And if so, like, what does that look like, right? Like, how do we make that happen? But yeah, that's effectively what we want to kind of ask ourselves. And that's what the question I want to answer first. So I need to be a little careful here. I wrote a diagram out, and I want to make sure that I can understand how to make this work. So let's see. So let's consider some coordinate vectors over here on the left-hand side. So if I have two bases, let's say that B and B prime are bases for V, then I can certainly express any vector in V in two different ways, right? I have a coordinate vector with respect to the first ordered basis, and I have a coordinate vector with respect to the second ordered basis. And we know how to transition between these two things. That's exactly the change of basis matrix P. Yep, here comes the diagram, exactly. And then, so we have this kind of similar thing over here, right? So same idea. We have a kind of a generalized coordinate vectors here with respect to b and b prime. And again, we know exactly how to convert between these things. It's exactly this change of basis matrix P. Now, what we're curious about is how to fill in these other gaps. And we've kind of seen how to do this in the last chapter. So there's actually a matrix action that will connect VB to VB. That's exactly this matrix. And then similarly, I can find a matrix for T with respect to basis B prime. And again, I have this way to connect these coordinate vectors using this kind of left-sided multiplication action. So basically, kind of looking at this commutative diagram, we can kind of see that there should be a relation between expressing T with respect to, say, like the standard basis B, for example, and representing T with respect to a different basis B prime. I just have to be able to navigate this diagram in a specific way. So that's what this next theorem is going to do. It's going to help us kind of navigate how we want to construct these two things, and it's going to show us this relationship between these two objects. So let T with respect to B be the matrix of our linear operator from V to V. And again, we're assuming a finite dimensional vector space here so that we have kind of a nice n by n matrix representation. And so the matrices that represent T for other ordered bases I'm going to call them B prime. Are given by the following. So let me write it down, and then we'll go back to our commutative diagram, and we'll kind of see why that happens to be the case. So I'm going to my claim is that TB should be equal to P TB prime P inverse. Shouldn't we have T for the second? Oh, the T's are missing in my diagram. Can I write them just as W's? I know what you mean, yeah. Yeah, I know what you mean. So I think in my monkey brain I was just like, oh, like I'm just going to land in some V in the vector space. I can represent it with coordinates in the following way. But yeah, these could be different. They could be the same, or they could be different vectors. I don't know, right? And the action of T acting on V is going to tell me what those output vectors look like. But yeah, that should be okay. Yeah, so I'm okay with that. So what we want to do is we want to say that this action here, so this movement in this direction, really should be equal to going P inverse. So we're going to be moving this way, then this way, and then this way. Right, so we're doing P inverse first, then we're connecting V and W with respect to the prime basis, which we know how to do, and then we're going to have P as our change of basis matrix as the last step. So we're not really proving anything here, we're just kind of summarizing all of the work that we've done previously, right? So we've already done all the work to find this change. We know that P exists, right? We know how to find this change of basis matrix. We know how to connect V with respect to B and W with respect to B. We know exactly how to do that. I know how to find that matrix. So there's nothing really to prove here. We're just kind of summarizing exactly all of the work that we've kind of done so far. Okay, so P is going to be a change of basis matrix. So P is our change of basis matrix from B prime to B. And I just want to make sure that that's correct. Yeah, it should be from B prime to B is the way that we, I tried to follow kind of what Artin did in the book. So that should be exactly the theorem that we're looking for. So this is interesting. This tells me that all of these matrices that can represent T, just with respect to different bases, they're all similar to each other. If you know what it means for matrices to be similar, it means they share similar determinants. They share similar traces, I think, as well, right? So like there's some nice properties that we get just from the fact that these matrix representations are similar to each other. So that's kind of cool. So that answers the first question. To me, that's all I really need to do. So that answers our first question. How do these matrix representations look? Well, to get from one to the other, I just need to find the change of basis matrix from the two bases that we're working with, and then do some kind of matrix multiplication. So to answer the second question, we're going to go off on a bit of a wild ride. So we're going to start with a definition. That definition is, let W be a subspace. I always want to write soup of a finite dimensional vector space V if T of W is contained in W as sets, then we say that W is T-invariant. Right, so here we're kind of thinking about, so this T is our linear operator, right? So we have this linear operator that's working on V, it's mapping V to itself, and if I can find a subset of vectors that kind of get mapped into themselves, we're just going to say they're T-invariant. And so the question is, like, how can I find these subspaces? What do these subspaces look like, and what kind of properties do they have? So how can we find such subspaces? So what we could do, I guess, is we could start by just analyzing what happens with a single vector. So is it possible for us to think about a single vector as kind of like a basis vector for a subspace, and we'll map it through T and we'll see where it goes. We'll try to force a particular property on it and see if we can get something as output. Kernels are T-invits true. Yes, so kernels and the range too, right? The range of our linear transformation should also be T-invariant. And I will leave that for the reader to prove a little bit later. Actually, we can probably just write that down now if you want. Yeah, so we can summarize that as a theorem. So 1, the kernel of T is T-invariant, and 2, the image of T is also T-invariant. And I'll leave that for you as an exercise to try. But yeah, you're right. So these two spaces are two examples of such subspaces. But I want to ask kind of a more general question. So yeah, we can certainly find a couple. So we know that these things exist. Certainly certainly V itself is a T-invariant subspace as well, right? Like if I take all of the vectors in vector space V and I map it through T. It's going to land, it's going to be contained inside of the original vector space. So there are some samples, right? So we know these things exist. I'm not just making up this definition for funsies. But what we want to do is we kind of want to think about like what happens with a single vector. Hi, Plaisant. Feels like we're looking for a kind of cyclic set of vectors. Yeah, I guess in some sense, right? Like in some sense, if we know that it's T-invariant, it should always be contained in W. So at worst, it's only getting smaller, right? As we iterate through T at worst. But at best, it could just be staying stable as well. I think we're going to go with an assumption here that are they going to be, I think that these T-invariant subspaces will be subspaces, although I don't think that's something that we can prove, at least that I'm not going to be thinking too much about right now. But will they be proper subspaces? Probably. I'm pretty sure that the T-invariant subspaces are subspaces in and of themselves, and we could probably prove it. Yeah. Yeah, that's what you're thinking? Yeah, exactly. So this brings up this idea of like nilpotency, for example, right? Like how many iterations do I have to go through to kill something, right? But yeah, so that's kind of like that. And there's a lot of different branches we can travel down just by thinking about T-invariant subspaces. That's a really interesting story, I think. And we're only going to see part of it. So what happens with a single vector? So what we should probably do is we should probably start by thinking about all of the vectors that get mapped to some multiple of themselves. Because if I think about a single vector and I think about all of the scalar multiples of that vector, that forms a subspace of the linear, of V, right? Like if I take any vector and I just think about the spanning set of that vector, that should be a subspace. So maybe I can find collections of vectors such that when I send them through T, they land in the spanning set, right, of that vector, right? So that's kind of what I'm thinking about. So this is like, I want to find the vectors. So we're trying to find V such that T of V lands in the spanning set, right? In the span of V, which we know is just all of the linear combinations of V. So this is kind of where we start. We're going to take a look at this equation and we're going to go, oh, okay, well, maybe I can find some vectors that do this, and what kind of properties do these vectors have? Yeah, okay, and maybe that, yeah, Stuki, thank you for the follow-up to that question. Yeah, you're right. The interesting invariant subspaces are exactly the proper, I gotcha, yeah. So we know that the full entire space, and we know that, of course, the zero vector itself should be T-invariant. But yeah, so if T has proper invariant subspaces, those are interesting things to think about. Yeah, I like that. That's why I like having you around, Stuki. You always pull in the good comments when we need them. Not all heroes wear capes, Stuki. So we've done a lot of this grunt work today to be able to rewrite this in terms of matrices, right? So what we're really going to do is we're going to, instead of thinking about T of V, let's actually just think about the matrix representation of T. So we're going to think about this in terms of matrices. So in terms of matrices, well, this T of V is really just left-sided multiplication, right, by some coordinate vector. And, maybe I should write this as, V with respect to some basis, but maybe we'll just convert this, right? So we're going to convert this vector V from vector space V into a coordinate vector. And we're going to be looking for any vectors X that satisfy this particular equation. So these are the things of interest. And we know that this is a realistic thing to do because of all of the legwork we've done in the last couple hours. So what we want to do here is maybe let's kind of move some stuff around. So maybe ax minus cx should be equal to the 0 vector, right? So we can maybe rewrite this as a homogeneous linear system. And of course we can maybe factor out x on the right-hand side, and we get something that looks like this. So just looking at this, and based on the conversation that we've had in the chat, yeah, we know that x equals 0 is going to satisfy this, right? We know that that's going to be one of those subspaces that's invariant. So that's maybe not an exciting thing to think about. So certainly if x is equal to the 0 vector, this is true. But we don't care about that. We're after the good stuff. We want the good stuff. So here's where things get a little tricky. We're going to say, okay, well, this is a homogeneous linear system. When does a homogeneous linear system have non-trivial solutions? It's going to have non-trivial solutions whenever the determinant of that coefficient matrix is identically equal to 0. So this is homogeneous linear system. So if the determinant of a minus ci is equal to 0, then we have the non-trivial solutions. So that's a big kind of key step here, right? When we're thinking about eigenvalues and eigenvectors, which is where the conversation kind of naturally lends itself to. So I'm just going to go ahead and summarize a couple of the key idea here. So 1, a value C in the field that we're working with, satisfying the determinant of a minus ci is equal to 0, gives a non-trivial solution. To the original problem that we're looking at, which is ax is equal to cx. And these values are called eigenvalues. And the second thing that we can tease apart from this is that for a fixed eigenvalue, any vectors that yield a solution, so the solution set of vectors satisfying a minus ci x is equal to 0. So any of these kind of non-zero vectors that satisfy this for a fixed eigenvalue are going to be in the null space. Why is that important? Because we know they're going to form a subspace. We know the null space should be a subspace. Okay, so that's a key thing to notice here. So now we're going to have a null space of a particular matrix. We know that these are going to be kind of naturally closed under the operations in question here. So we might be able to glean some subspaces out of this problem that might be T-invariant. And we should be able to find a basis for this set of vectors. So that's also kind of important. Okay, so any X that satisfies that original problem of AX equals CX is called an eigenvector that corresponds with a particular C. Okay, so all of these, this collection of vectors for a fixed eigenvalue is called an eigenvector corresponding to C. I don't like putting that here. It's these vectors here, right? So these vectors are the eigenvectors. Corresponding to C. And because they're a subspace, I should be able to pick out a couple of those vectors, form a basis, and maybe this basis is going to be something interesting for us to look at, is kind of the end goal here. Okay, so I don't know how much of this I want to do. Yes. Hi, Sensation. What can I do for you? Never letting that go? Okay. Then I'm never going to give you up. I'll never run around or desert you, Sensation. Okay, let's get this filter off here. I'm just going to do some quick calculations with a 3x3 so that we can find some eigenvalues and eigenvectors, just in case there are some people that are inside the reading group that need this as a little bit of a refresher. So for example, let's let A be equal to 0, 0, minus 2, 1, 2, 1, and 1, 0, and 3. So we can form A minus Ci by just doing a subtraction along the main diagonal. And then we can go ahead and calculate the determinant. So the determinant of A minus Ci, we kind of want to look at when this is equal to 0. So I'm going to skip a little bit of the proof here, but we do get something that looks like this. So I get that C minus 2, C minus 2, and C minus 1 is equal to 0. So this here is called the characteristic polynomial. I just happen to have it in factored form. And then this whole equation is called the characteristic equation. But the idea is, like, if I can factor the characteristic polynomial over the field that I'm working in and find those factors, then those specific factors should be the eigenvalues that we're looking for. So we have C is equal to 1 and C is equal to 2. These are our eigenvalues for matrix A. And then the process is really just taking those values for C, plugging them back into the A minus Ci, and kind of expanding this to homogeneous linear system. So what I'll do is I'll solve one of these so you can kind of see my thought process. So for C is equal to 1, for example, what we're going to do is we're going to look at A minus 1 times I, and we're going to look at this particular matrix, which should come out looking like this, and 1, 0, 2. So I'm just kind of scrolling back here. Anywhere that I see C on the main diagonal, I'm just going to input the number 1, and then just simplify that matrix. And I get something that looks like this. And remember, what we want is we want the reduced row echelon form. So we can go through a little bit of work to get the reduced row echelon form. I'm not going to show you that work. Since I feel like most of those who are in the art and reading group have probably taken an introductory linear algebra course, so you've probably done a little bit of this work already. And then what we want to do is we want to look at what this reduced row echelon form is giving to us. So in this particular case, what do we get? We can kind of glean that if we label this as maybe x, y, and z, our three variables, then we get that x plus 2z is 0, and we get that y minus z is 0. So there's a relationship here that says x should be equivalent to negative 2z, and y should be equivalent to z. So when I go to construct my eigenvectors, which should come in R3 in this particular case, I know that x needs to be negative 2z, I know that y needs to be z, and I know that z here is the free parameter. It does not have a leading one in the reduced or echelon form. So all of my eigenvectors are going to look something like this. So if I factor out that kind of z component, I get negative 2, 1, and 1 times some kind of free variable. I'm allowed to kind of pick z here to be whatever it wants. So it's this negative 2, 1, and 1 that's of interest to us. This is exactly the basis vector for this particular, we call it an eigenspace. And it's a basis because there's only one vector, so it's linearly independent, and you can see that it spans the space, right? So all of the eigenvectors have the form negative 2z, z, z, and I can take this basis vector and I can multiply it by z, right? Some kind of scalar number, and I can recapture all of the information that I need. So it's a linearly independent spanning set, so it's got to be a basis for the eigenvectors. Of this particular form. Now, I mean, theoretically, we can argue a little bit here that maybe z shouldn't be 0 because we don't want this to be identically equal to 0, because otherwise, you know, maybe we don't care about that because it's not interesting. But I mean, the idea here is that this is a subspace, right, of R3, and I know that the 0 vector has to be a part of that subspace. So whether or not we choose to include z is equal to 0 or not, I still need to include the 0 vector as part of that span, right? I still need that to be a spanning set and to be a nice subspace of the space that I'm working with. So I'm just going to kind of intuitively argue here that z equals 0 is okay in this particular case when we're thinking about the subspace as a whole. Now, something interesting happens when we go to look at c is equal to 2. And I'm not going to go through the full process here, but we do get an RREF here that looks something like this. So we're just going to skip right to the RREF, which is this. And so in this particular case, this implies that x plus z is equal to 0, or the only relationship that we have is that x needs to be equal to negative z. So when I go to construct my eigenvectors, I get something that looks like this. X has to be minus z. I have no relationship for y. Y is a free variable, and I also have z as a free variable. So this is now what my eigenvectors look like for c is equal to 2. Which is kind of interesting. Yeah, so fem exactly, yeah. So this past one is a one-dimensional eigenspace. Yeah, left as an exercise for the reader, exactly. So in this particular case, we can use properties in R3 to bust this down a little bit, and we could say something like this. We could say, okay, well, let's take a look at all of the stuff that has a z in it, and let's add to that all of the stuff that has a y in it. All right, so we should be able to do this. And we should be able to kind of factor out that z to get minus 1, 0, 1. And we should be able to factor out this y to get 0, 1, 0. So in some sense, this is an interesting example because now we have a subspace that's more than one-dimensional. This one's actually two-dimensional. And we can see that these two basis vectors that we're going to grab are linearly independent, right? So these two vectors, I can quickly see they're not scalar multiples of each other, so they happen to be linearly independent. They span my space. So these are the exact candidates that I need for a basis for this particular space. Okay, so we can grab these vectors. These are going to form our basis. For the space that looks like this, negative z, y, and z. So there you go. That gives you kind of a more numerical example, something we can kind of grasp and hold on to, showing you how we find these subspaces and how we look at trying to find these basis vectors. Hi, Phobos. Welcome back. Now, one question that was really bothering me when I was kind of going back through, looking at my notes, was the following. I was like, okay, like, can I just union all of these subspaces together in some sense? Like, if I grab, like, all of these basis vectors, I should say, can I just smack them all together into a bigger set? And do all of these basis vectors have this nice property of linear independence? So that was the big question that I wanted to ask myself. So here's my proposition. My proposition is that the union of linearly independent basis vectors corresponding to our distinct eigenvalues they remain linearly independent. So that's kind of interesting. That's interesting. Now, there's a couple things that we are going to need here. We do need distinct eigenvalues. So when I was looking through a lot of these proofs, I think like the idea was, I have an eigenvalue, a single eigenvector probably pops out of dimension 1, and then it's really easy to kind of see that all of these things, when we union them together, becomes linearly independent. So there's a little bit of trickery that probably happens here when we don't quite have enough, or we have like, in this particular example, we had like a repeated eigenvalue. So there's maybe a little bit more that I have to think about, but this is what I was able to kind of come down to with the short amount of time that I had to look over some stuff. But this to me feels important, right? So let's get some assumptions rolling here. So let V1, V2, up to Vk be our eigenvectors with corresponding eigenvalues, and we're going to call those corresponding distinct eigenvalues, let's say, so we don't want to get a 0 here. Okay, so we're just going to label, maybe let's label this up to CK. Okay, so I have a specific eigenvector that maybe is corresponding with a specific distinct eigenvalue. So in some sense, if I'm given these kind of k distinct eigenvalues, and I can grab at least one vector that corresponds with these distinct eigenvalues, then these should all be linearly independent, is what we're going to be trying to prove. So let's go ahead, let's consider V1 plus V2 all the way up to Vk is equal to the 0 vector. And we're going to proceed by induction on k. So when, let's see, when k is equal to 1, I have a single vector. And so this is, we have that v1 is equal to 0, and so our base case is true. So now what we want to do is we want to start with our induction on k and see what happens as we start adding more and more of these particular vectors. Okay, so now when k is bigger than 1, there's a couple things that happen. What am I writing down here? Yes, that seems to be true. And we can left multiply here. That leads to that. And then we do a subtraction. Okay. Okay, I saw something pop up in the chat, so give me a hot second to write something down. You need to consider a linear combination, not a sum. How does this work? That's what we're going to be doing here. We're going to be looking at the linear combinations, right? So, okay, give me a hot second here to think about this. So, I think that the sum of the vectors here, I think it's an equivalent condition, isn't it? Or if all of these are identically equal to 0, this would force all of our vectors to be equal to 0, right? So it's an equivalent condition to looking at a linear combination, if I remember correctly. Isn't it like if this implies that every single vector is 0? I think this is what we're working with. We're working with like if the sum of all of our vectors is 0 implies the only solution is that each vi is equal to 0. Then they're independent, right? So it's a bit of a weird way. I agree with you. I wouldn't normally think through a proof this way. No, it's a little different. I think I'm trying to, so I think from what I was reading, they're trying to use this, right? And it should be equivalent to linear independence using scalars, but instead of using scalars, we're going to look at the sum of the vectors, and what we need to do is we need to force all of these vectors to be the 0 vector. So if I could show that the only solution is the 0 vector, then I know that these things are independent. That all of these vectors are forced to be the 0 vector. So it's equivalent, from my perspective, it feels equivalent to if I have a sum of ki vi equal to 0, this implies all of the ki's are equal to 0. It feels equivalent to me. But I'm happy to be corrected if I'm wrong. So it feels like in one sense you're forcing all of the vi's to be fixed, and then you're looking at the scalar multiples and you're saying, okay, well, if all the scalar multiples are 0, then this is the result. And in the other way, you're saying, let's just fix all of the ki's to be 1, right? And if the only solution to this problem is that each one of these vectors is the 0 vector, then they have to be independent. Seems to be true for eigenvectors. Wasn't this in Artin? I could be wrong, but I feel like this was in Artin somewhere. It's worthwhile for us to figure this out, because it's going to be... It's the only way that I know realistically how to prove this thing. Vector spaces, basis and dimension. This, I think he talked about it in like the independent section. So real vector spaces, abstract fields, basis and dimension. Maybe it was inside here. Linear relation. Yeah, so that's one way that we usually think about independence. Darn, I wish I would have written down a little bit more, because I read this and I was like, oh, that's exactly the thing that I need. Yeah, that I remember all of that stuff. That's the dimension. Darn, okay, I thought I saw it in Artin somewhere. Maybe I'm just going crazy. Is this in the direct sum section? Here it is. Oh, it's in the direct sum section. Yeah. Here it is. It's right here. So maybe it needs a little bit more legwork for me to be able to verify. But yeah, so the set of all such vectors is called the sum of the subspaces of their span. So we create a vector that is an addition of all of these vectors. And then so the subspaces are called independent if no sum with the is 0. Right, okay, so I need to use this, right? So I'm using a little bit more extra firepower, I guess. Right, so we're checking to see if all of these subspaces are independent of each other. So maybe I need to, let's port this over. So it's called the sum, so we're using this here, right? So, okay, so right, so we're using this from Artin. So it's a little bit different from what my intuition had said. But we know that these are all subspaces, so we should be able to utilize this particular idea in Artin to get the job done. Okay, so my apologies there for being a little bit off, but we're using this idea here. Okay, so if I can show that this equation implies that all of these vectors are 0, then the subspaces themselves are independent, right? Which means they should have independent basis vectors. Yeah, so maybe it's true. I think you're right. It's not true in the general case, but in this particular case, I know that each one of these vectors that we're taking is a vector from a subspace, and that's, I think, the important part here. Yeah, it's a vector from a subspace, so that when I add these up and equate it to 0, I can get independence of these subspaces by looking at this particular equation. Let me know if that makes sense, or if we need to chat a little bit more around that. I'm happy to chat a little bit more around that if we need to. put a little star here. What page is that? So if you want to read that in Arten, it's page 102. And so you are right that it shouldn't work in the general case, but it should work for the eigenvectors that we're working with, because each one of them individually forms a subspace. Yeah. Yeah, so this is definitely a direct sum path, and my apologies for not being immediately clear that that is the case. Okay, so what I did after I kind of found this was to think about that sum. We're going to scalar multiply it by C1, and that's going to give us something that looks like this, which should be equal to our 0 vector in V. And then the next thing that we can do is we can left side multiply equation 1 by some matrix A. So let's go ahead and left multiply. And if we go ahead and multiply through, we're just going to get like AV1. We know what that looks like. We know what AV2 looks like, and so on up to AVK. Of course, this remains the 0 vector over here. And then each of these AVIs gets mapped to C times that particular thing by the action of A on that particular eigenvector. So we get C1V1 plus C2V2 and so on up to CKVK. So now we have a couple other things that we have to work with at our disposal. Ander says, maybe it's worth mentioning here that we're taking the image of T as the direct sum, not necessarily all of V. Yeah, because we're doing the, yeah, exactly. Because we're doing the left-sided multiplication by A, all of these vectors that we're really working with are inside of V. I agree with you, yeah. At least all of these scalar multiplied vectors too, right? So you're saying that these as well, yeah, okay, so these V's as well should be inside of vector space W, which is the image space. Yeah, I gotcha. Yeah, I'm okay with that. All right, so let's go ahead and subtract 1 and 2 from each other. And we get the following. So we should get C1V1 minus C1V1, so that's just 0. And then we will get C1V2 minus C2V2, so we get C1 minus C2 V2, and so on until we get to C1 minus CK VK. And then, of course, the subtraction of the 0 vectors here should give us the 0 vector as well. And now we are just going to use this idea that all of these C's have to be distinct. So none of these are equal to 0. So that's really going to force one particular solution, and that's that all of our V's here are going to be identically equal to 0. Okay, so an induction on K should get the job done here. That's not saying if it's invertible. Diagonalizable doesn't imply. Yeah, we need to also. You need to have non-zero eigenvalues too, right? For invertibility. All right. So if I have all of these distinct eigenvalues and I can grab an eigenvector that corresponds with each one of those distinct eigenvalues, then I know that that collection of vectors should be linearly independent, right? And all of these kind of subspaces are independent of each other in a very, very kind of nice, organized way. And as a corollary, basically we're going to say that, we can form a basis basically for Fn if I know that I have n distinct eigenvalues. So that's really nice. So in the nicest sense, if I take my matrix that represents the linear transformation and I can find n distinct eigenvalues, I know that I have an easy way to move forward. I know that we have a basis for Fn, and we're going to be able to show that our matrix is diagonalizable. Yeah, exactly. So Ultimate is asking a good follow-up question. Does that mean our matrix has full rank? And the answer, I believe, is going to be yes in that case. Well, I have to be a little careful here. Not necessarily Ultimate. I think if we have an eigenvalue of 0, we run into a problem. So I think it's less about A having full rank and more about 0 not being an eigenvalue. Because if we go to diagonalize and we have 0 along the main diagonal, we know the determinant is 0 for that matrix. So we have a singular matrix. And I think we're going to run into problems with the rank, right, in the reducer echelon form. So hopefully that clears it. So maybe not. Yeah, maybe not. Now, what we do get, though, is if 0 happens to be an eigenvalue, I know that then I can find a non-zero eigenvector that forms a basis for that subspace. So even though the matrix could be singular, I still should be able to get a corresponding eigenvector that's going to help me get a basis for Fn. So there is a little bit of a non-intuitive gap here, I think, right? Like the eigenvalue of 0 does form a bit of a problem, but I still should be able to find a non-zero vector that I can use as a basis if c is equal to 0 in this case. Is an eigenvalue of 0 a sane thing? Yeah, it means that a whole group of vectors gets flattened. So but you're going to lose dimension. You're going to lose dimensionality if you get c is equal to 0 as an eigenvalue. All right, so this leads us to what I would consider the important part of the discussion. We have n linearly independent vectors, and we can arrange them into some kind of matrix, and this allows us to create an interesting change of basis matrix. So we can basically arrange all of these vectors as columns. And now we have this interesting change of basis matrix that's going to allow us to do a little bit of work with regards to the representation for our linear transformation. So these are our linearly independent vectors. And we can think about this as a change of basis. Right, we're changing into what we call, like, what I would call an eigenbasis, rather than maybe a standard basis that I might pick. So in some sense, this collection of eigenvectors is an interesting basis to pick, and it has some really nice properties. So let me just kind of jot some of that down. So we recognize I'm going to recognize this as a change of basis matrix. Right, these are linearly independent, so it should have an inverse. And P has always taken us from B prime to B. So B prime in this case is the what we call the eigenbasis. And kind of in the background, the tools that we were using are like everything's been done in the standard basis with our analysis. So this matrix P should convert us from the eigenbasis that we have back to our standard basis. And then we're just going to go ahead and we're going to multiply A by P. So if we go ahead and left side multiply by A, we should end up getting something that looks like this as our columns. Now this left-sided multiplication is going to convert all of our columns into things like C1, V1, right? So the we have this equivalent expression here due to that relationship that we have with A, C,
Following
and
the
V, right?
conventions of notation in Artins,
These are
is
all
P always with respect
eigenvectors.
to the canonical basis of Fn?
Following the conventions of is Artins P always with respect to the canonical basis. So P is always a change of basis from the, I think he's usually going from like a non-standard basis to the standard basis typically, is how I think about P. Although the inverse does the opposite. So it's, you know, you can theoretically create a change of basis in any direction that you want by either observing P or P inverse. But yeah, I assume that Artin's always doing everything with regards to the standard basis as kind of the place we're going to. At least that, from my perspective, that makes a lot of the computations easier to work with. Okay, so Ci here are eigenvalues. And the interesting part now becomes our ability to rewrite this in terms of a diagonal matrix representation. So what we can actually do now is we can think about this as a matrix that consists of our eigenvectors as columns. And what we get on the right-hand side is a multiplication by what we call a diagonal matrix. Okay, so this is a diagonal matrix. All of the other entries off the main diagonal are 0. Okay, so A times P. So basically what we have is we have A times P is equal to P times D, right? Where D is some diagonal matrix. Yeah, Placente's right. As soon as you have a 0 eigenvalue, then you're into a non-zero kernel, exactly. And that's always the case that we have to be a little careful about. But just because we have a 0 eigenvalue doesn't mean that we cannot form this matrix P, right? It still should have an associated eigenvector that's not 0, and this should still be this should still be linearly independent, right? So this change of basis, it should still work, despite the fact that we have a singular matrix representation for our linear transformation. Right, so we have kind of the following, and of course we can rearrange this to get a diagonal matrix in terms of matrix A. So that's going to be the theorem that we pop out here after doing a little bit of legwork here with regards to our eigenspaces. So this is the big one. That is if an n by n matrix has n distinct eigenvalues, then we know that we have the following relationship where D is equal to P inverse AP, or vice versa. We could write it as PD, P inverse is equal to A. So this is going to be a diagonal matrix, and the eigenvalues, so this is going to be consisting of the eigenvalues on the main diagonal. And we know exactly what P looks like. P is the columns, and each of the columns in P is going to be the eigenvectors that we found from all of those particular eigenspaces. So P consists of the corresponding eigenvectors. And I mean, specifically, we're kind of taking the basis vectors. And we want to take those eigenvectors as columns. Yeah, Reese is here. He's about ready for dinner, so we got to wrap this up pretty soon, my friends. But I got just like a couple more interesting things to potentially chat about. We talked about the other T-invariant subspaces. The last thing I really want to show you is that with regards to the eigenspaces that we're working with, the eigenspaces are all T-invariant. Oh god. That's a good clip, Anders. That's a good clip to get for sure. So, like I said, this is the kind of the last little bit that I want to give to you for today, and that is if. Hi, Andy. Welcome in. He was just out.
Hello there.
General Kenobi!
I'm so happy that you clipped that. Yeah, Reese definitely wants some food, so we will we'll tend to Reese. We'll get him out for a walk. But I want to leave you with this, and this is kind of the start, I think, of where the conversation goes, right? So we have these eigenspaces. We have these kind of basis vectors that we can work with. It turns out that these eigenspaces are T-invariant subspaces of our map, and it's not really hard to prove that. So I'm going to go ahead and prove that for you. And I think generally where the conversation tends to go after this is, okay, so if I have a proper T-invariant subspace, how do I break that up into a direct sum of these other kind of smaller, or how can I break it up maybe into smaller T-invariant subspaces? And I'm pretty sure that the eigenspaces play a really crucial role in the direct sum of these T-invariant subspaces. Yeah, so all of our eigenspaces, in the general sense, the ones that we've worked with here, are going to be T-invariant, and it's not too hard to prove that, so all we want to do is we want to check what happens to these particular vectors. So let's take a V that's inside of EC, so V is inside of EC. So we know, for example, that T evaluated at V should come out to be C times V, right? So we have this kind of scaling factor that happens to these particular vectors that are a part of EC. So since T is a linear operator, we know that we can bring T out of this particular map, and then we know exactly what happens to T of V. It just gets stretched by a factor of C. So what we want to do is we just want to check that this particular property holds, and it does. We can just kind of rearrange our scalars here to get what we want, right? So now we have that the vector kv gets scaled by factor of c as it moves through this linear operator. And similarly, if we grab a couple of vectors, so let's take let's take v and w inside of EC. We can do the same thing here. So let's take a look at the sum of these things. So the sum of two vectors that are inside this eigenspace through t should get mapped to t of v plus t of w. And then since these are eigenvectors, they should get stretched by some factor of c, right? So we get something that looks like this. And this is really just c times v plus w. Right, so again, we see that this vector gets scaled up by a factor of c, so it is indeed still inside the eigenspace. So we see that the eigenspace is T invariant. So there you go. I think that's all I really wanted to talk about today. And like I said, there's a really interesting conversation that's, I think, very kind of closely related to group theory with regards to these T-invariant subspaces and how these eigenspaces help us decompose the invariant subspaces in some way. I couldn't get more information on this, so this is probably where I kind of have to stop the conversation with regards to that for today. But hopefully that gives you a good indicator of some of the paths that we can follow, right? We still really haven't talked a lot about the kernel, right? Like proper, like non-zero subspaces of the kernel. We still haven't talked about anything with the range or the image of T. So there's a lot of paths you can follow, and that's really kind of what a higher order linear algebra class is supposed to kind of think about, right? These are the topics that are, I think, really interesting to think about with regards to vector spaces. Yeah. Oh God, Reese. Oh, yuck. St. Bernard has a lot of slobbering. He definitely slobbered all over my monitor. Yeah, Arten's a little bit of a mad lad. Like, Arten literally speedruns linear algebra part 2 and part 3 in like one chapter. And I tried to do my best to summarize that in 3 hours. But normally if I was teaching this to a class, we would spend a lot more time being very careful in how we construct these things. But hopefully I was able to give you an interesting story, right? Like that was my goal today, was to show you an interesting story about, you know, natural maps, natural isomorphisms that occur between our vector spaces and our coordinate vector spaces in Fn. There's a natural map called that linear transformation that connects kind of horizontally between vector spaces, and then you can kind of connect your Fn and Fm spaces that way and talk about properties down there. And then the last, I think, interesting story is to talk about these invariant spaces under a linear map, and that to me leads to the big discussion about, you know, why are eigenvalues and eigenvectors important? Well, because they happen to be the fundamental, they start to become the fundamental building blocks of these T-invariant subspaces that we want to talk about. Yeah. It is a speed run. Doing this in 3 hours, that felt like a speed run. Like, I'm gonna go drink now, guys. Like, I'm gonna peace out. I'm gonna go have a couple cocktails. I'm gonna enjoy my Sunday night. Yeah, exactly, Anders. I saw it too. When you start to talk about Jordan form, you start talking about it's not just A minus Ci anymore. Now it becomes like A minus Ci squared or A minus Ci cubed, right? And so you start looking at powers of that matrix, and yes, it starts to become a cyclic operator, and we're trying to look at how many times do I have to repeat that process until I hit the identity operation. So yeah, Jordan forms are completely based around, I think cyclic groups is what it feels natural to talk about, but there's something about cycling through that matrix and landing on the identity that's important, right? And you have to find that kind of like lowest power that hits the identity. Yeah. So there's some really cool connections, right? And so to me, the T-invariant subspaces kind of connect to direct sum or external direct products a little bit. We've seen the natural connections today to isomorphisms and homeomorphisms. And I'm sure there's others, right? Like what we're doing today is a lot of modeling with the addition operator. But I'd be curious to know about these vector spaces where multiplication now becomes like the primary operator that we're working with, right? Like you can really spin this off and explore a lot of really interesting stuff. Yeah. And so this is as we end stream today, this is my shameless plug to everyone that is in attendance right now. So Zach and I, of course, Zach and I are going to be hosting a linear algebra course, and that's going to be happening in January. So here we are teaming up, and we're going to be co-teaching a linear algebra course starting mid-January. Our goal is to start with the fundamentals of linear transformation. So what do linear transformations do between vector spaces? And we're just going to see where the story goes. Like, where does the story go if we start with linear transformations? We are not starting with vectors. We are not starting with matrices. We are starting with linear transformations. And where does that story go? And how realistically, how do all of the matrix operations and vector operations that we do and normally study in linear algebra 1, how do they fall out of this viewpoint of thinking about linear transformations? Yeah. Hyped to learn about T-invariant subspaces. Yeah, I would love to learn a bit more.
One slap, you're gonna love my nuts. Two slaps, you're gonna love my nuts.
It's nuts on there. That's so
you're gonna
nuts.
love my nuts. Hate my nuts. Watch my nuts. Slap my nuts. I love my nuts. Gonna make America love my nuts. One slap at a time.
Lucas, if you posted your question on Discord, I'll take a look at it, but I want to kind of cut this off so I can port this over to YouTube for the simple group in case I want to take a look at the speed run of linear algebra. But yeah, if you posted it up on Discord, I'll take a look at it and I'll respond back to you here over my next cocktail. And yeah, if anyone has a good source for T-invariant subspaces of a vector space, I would love to get that source. I should check to see if Friedberg has anything on these T-invariant subspaces, but I would also be curious to know more, because my major question is, how hard is it for us to prove that any T-invariant subspace is a direct sum or direct product in some sense, right? An external direct product of eigenspaces. To me, that's the interesting conclusion to that story, and I don't know how to connect those two gaps yet. So that's where I want to learn a bit more personally. Is anyone online right now? Thank you very much, Fem. I'm glad you had a good evening. Is anyone online that we can raid right now? Is it a prime decomposition theorem? Ooh, I don't know.
Said it right. Prime decomposition theorem states every integer has a unique prime factorization. What zeta math concept will we tackle next?
Good cocktails, yes. And Anders and Plaisant, I will... No, not that. Wrong one, show. Wrong one. I will drop off a couple QED points for you guys.
Problem solved.
Ooh, ultimate. Yeah, we can take a look at that. And then we want to get Plaisant in here as well as a thank you.
QED.
For reminding me.
Final GPT%.
I wanted to thank you for reminding me that we had to use a little bit of that backbone and Arton to get the job done for the linear independence. So Cat Vinel, a vanilla cat. That's not correct. That is not correct. Oh my god. Andy, I have a funny story for you if you're still here. Invalid username. Oh, maybe I don't have to put the at. Cool, let's go raid Kate and say hello. Hopefully they're doing maths or some kind of science. And hopefully they're not hot tub streaming. Hopefully Ultimate Doom has not made us go into a hot tub stream tonight. Alright, bye guys. I will see you probably at some point tomorrow. Abstract Algebra is going to be canceled for the night because Dave and I are going out to have some cocktails. And yeah, maybe I'll see you tomorrow night.
But you'll thank me
for
when
some
you
abstract
realize
algebra.
how much brilliance
Until
I bring
then,
to the
take care,
table.
folks.
A genius like me is rare. Grasp it while you can.
We'll talk to you guys later. Bye.